two topological spaces, X endowed with a topology F and Y endowed with a topology R, are called homeomorphic, spelled hom-e-o-morphic. They're homeomorphic if there exists a function h from x to y that has three properties. So the first is h needs to be a bijection. And just to remind you, I'm saying it's one-to-one and onto. Okay, so h from x to y is a bijection. I need to know that h, which maps from x to y, I want this to be continuous in the sense that we just talked about. So any open set of y, its preimage under h is an open set of x. And then finally, I need to assume that the inverse function, h inverse, which by the way, that's a function from y to x, and just because I'm assuming h is a bijection, I know it has an inverse function. I want to assume that h inverse is also continuous. So those are the three properties that I need to have a homeomorphism. We call h a homeomorphism, which I've written in the remarks below, so I'll wait to get to that. Just to be clear, in case you've forgotten, I want to remind you how h inverse is defined. So h inverse of little a is b if and only if little h of b is a. This is exactly the definition that we use in Calc 1, college algebra. Same thing you've seen, same basic idea. And I just need to assume that I have a bijection that not only is h continuous, but its inverse is also continuous as well. And some of you are rightly asking, and this is a good question that I hope you're thinking about, if I know these two, isn't that enough to know that this is also going to be continuous? And the answer is actually no. I would encourage you to Google, if you want to, that's fine. Google a bijective continuous function that is not homeomorphic. And I think you can either Google it, or I bet if you play around with maybe the discrete topology, the examples that we did before, flip the roles, and I bet you can come up with one. So certainly you can find functions that are bijective. H is continuous, but its inverse isn't continuous. All right. Oh, and I already, man, I'm kind of messing things up here. I already mentioned to you the definition of the inverse. I got that over there. So first remark, already said it. I'll say it again. The function h is called a homeomorphism. And so when you have a homeomorphism between two spaces, they are called homeomorphic. And so how should you think about homeomorphic spaces? Well, two spaces are homeomorphic if they are, I'm just going to put in quotes, the same, but we're going to go ahead and say topologically. So they're topologically the same. And this is getting at that notion that we talked about on that one, I'll call it a fun day for lack of a better word, but when we discussed the fact that topology doesn't care about maybe distance, for example. It cares about those properties of shape which don't change under stretching and shrinking and so on and so forth. And so for us, we're not saying they're the same in every sense. We're saying they're the same topologically. So homeomorphisms allow you to conclude that, hey, this space is really topologically the same as the other space. I do want to make a third observation with you, and then we'll break the video and go on to the next part. So just think with me. If you have two different sets, x and y, and they have different, I spelled my writing for different was pretty horrible. Let's rewrite that. They have different cardinalities. Maybe they're both finite and x has 5 elements and y only has 3. Maybe x is countable and y is uncountable. Whatever. If they have different cardinalities, then you automatically know that no space, let's say x and then some topology f, and y, some topology r, can be homeomorphic. And why is that? Well, because you need a bijection from x to y, and if they have different cardinalities, you're not going to get a bijection. So that is just an important observation to be aware of. So let's break this video here, and then in the next one, we're going to look at an example, and we'll play around with this.